Welcome to the third lecture of the master course Renewables in Electricity Markets. Today, we are going to talk about only day-ahead markets. So, first, we have a recap, 5 minutes recap. So these are the main keywords I collected from previous lecture on fundamentals of electricity markets. So, yeah, most of the keywords from last lecture, I think they are there. So I suggest that for the next 5 minutes, talk to your friend and try to remember what you learned from the last lecture. And then we will move on to the new lecture on day-ahead markets. Let's review together quickly. So there are 4 main items. First is various market actors. We talked about different actors or market participants. The first one that we talked is power producers, those who produce power. Can you give me a few examples of power producers in Denmark? Or still, for example, one. Very good. Or are you familiar with the biggest power producer in France, for example? What is that? EDF, right? Good. Second is power demands. Can you give me an example of power demands? The power demands are either large-scale industrial plants, large consumers, not necessarily industrial, it might be commercial or whatever, but big demands. Or they are, what's the keyword I'm looking for? Yes? No, we talked about one word. Retailer. Do you remember retailer? Retailers are power demands. And through, for example, the website, lpris.dk, you can choose your retailer. So who is a retailer? What is the task of a retailer? Yes?
Like being the middle person between the market and the household consumers.
It's a middle person or between the market, electricity market, and end users. So retailers, they buy power in bulk, in big volume from markets and sell it back to the small consumers, like residential houses. We talked about market operator. Is a market operator an entity for profit? No, it's non-profit entity who clears the market, right? Can you give me an example of a market operator for day-ahead and day-ahead and intraday markets in Nordics? Like Nord Pool or Apex. Then we talked about system operators, TSO and DSOs. TSO is responsible for what? Don't be shy. TSO is responsible for?
Balancing.
No, the safe operation of what? The safe operation of high voltage transmission grid, right? Good. Is there any market that TSO clears? Not day ahead, not intraday, balancing market. And to make sure that we have enough resources in the balancing stage, close to real time, to make sure that we have enough resources to activate them for up-regulation or down-regulation, what market else also TSO runs a day before? Ancillary service markets, the reserve markets. Very good. Then we talked about market regulator, who monitors, observes the market and the performance of the market and sets the rules and policies. It does regulation. And traders. Traders are those who buy power and sell between markets. It could be the same market or different markets. For example, buying and selling in the intraday market or between day-ahead and intraday markets, or between intraday and balancing markets, and so forth. So it's a middle person between markets, and it's for profit. A trader could be purely financial, meaning that it has no physical asset, or it could have an asset like a battery. Good. Then we talked about various types of electricity markets. We talked about capacity markets that we will not cover in this course. Can you remind me what is the commodity we trade in capacity market? What's the unit? Megawatt. It's capacity. So in the capacity market, we pay producers as long as they bid in the market, no matter their bid will be accepted or not. Why do we do that? Why should we pay, especially the expensive generators, for their availability? Do you remember we discussed that? Yes? Yeah, please.
Incentivize the investments in capacity.
Yes. To make sure that in short term and also specifically long term, we will have enough capacity in the market. It's for security of supply. And this is important, especially for generators who are not often scheduled in the market if they are expensive, like gas units. Good. Then we talked about energy markets. So what is the commodity we trade in energy market? What is the unit? Megawatt hour. It's energy. So we will talk more about energy market. Then we talked about ancillary service markets, that TSO runs it to make sure that they have enough flexibility resources in the balancing stage. Futures markets. It's a market for energy. We are not going to cover it in this course, but can you remind me, what is the time span? So when you buy or sell power in futures markets, is it for the next day or? So what's up to 6 years? From, let's say, 6 months to 6 years. It's a purely financial market. Can you remind me where, or if you would like to buy or sell power in futures market, where should you go? What is the platform? It's NASDAQ. Good. Then day-ahead market. I don't want to discuss it because the whole lecture today, we are going to talk about day-ahead market. Then intraday market, which is being cleared after day-ahead market, right? So why do we need intraday market? So we said that if you yes, please.
So if your projections might change for like a wind producer, you can align with that.
If you have an updated projection, updated forecast for your wind production, for your demand, if you are a retailer, or for trading purposes, then you can go intraday market and try to modify your day-ahead position. For example, if you already, I don't know, sold 10 megawatt in the day-ahead market for a specific hour, you may go and buy one more or sell one more megawatt. So it becomes 11 in total. Good. And balancing market. We just said that it's the TSO clears that market. It's to make sure that the system, the grid, works perfectly. There is power supply and power demand balance. We are going to talk about intraday and balancing markets in 2 lectures from today. Good. Then we talked about European versus US electricity markets. We talk about these 2 because it's like the type of the markets. There are also many other electricity markets in different parts of the world, but usually they pick one of these 2 styles. Though it's not necessarily always the case. For example, the market in Australia is kind of its own style, but I'm not covering that here. Okay, so in terms of differences, the first one is Nodal versus Zonal. Which market, which type of markets use Nodal setup? US or European? US. Nodals means that they represent the transmission network as it is. So the capacity, the topology of the transmission network and the capacity of transmission lines are represented in the market clearing problem. While it's not the case in Europe. How is it in Europe? It's zonal. It's zonal. So we discussed that in Europe we have bidding zones, and all the transmission line constraints inside the bidding zone are disregarded. It's not 100% correct. We will see it today, but let's have it for now. Okay? So for example, in Denmark, how many bidding zones do we have? 2. DK1, DK2. Good. Copenhagen is part of DK1 or DK2? DK2. Very good. ISO versus TSO. Well, are all markets in Europe being cleared by the market operator, by Nord Pool? No. Day ahead and intraday are by market operator, but the one who operates the grid is the TSO. And the TSO runs the balancing market, right? So there are two different entities for market operation and for system operation. While in US, it's ISO, Independent System Operator, like CAISO, the California ISO, or PJM ISO, or New England ISO. They run the market and run the grid. Clear? Then energy and reserve dispatch. Since in US it's one entity doing all the job, ISO, then we have co-optimization, a joint market for trading energy and buying reserve. So ISO does that in the same joint market. While in Europe, there are two different entities. So TSO is the one who buys reserve. Market operator is the one who trades energy, so there is no joint market. The markets are sequential. First reserve market, then day-ahead intraday markets. Clear? Also, we discussed about complexity of bits and complexity of markets. We discussed that in Europe. You are, as a generator, you are responsible to internalize your technical constraints within your bits. That's why you're allowed to submit something called block orders. It's the offers that connect different time periods. For example, you say from hour X to hour Y, I'm going to produce every hour 2 megawatt at the average price of Y. So the bid should be either fully accepted or fully rejected. While in US, no, the generators, they also submit their technical constraints like ramp rate, minimum uptime, all the constraints that we call them unit commitment constraints to the market operator, to ISO. Are you following? Very good. Then we did a bit of math. We wrote the market clearing problem as a linear optimization problem. We learned about the concept of dual variable. We discussed why dual variable of power balance equality gives us the market price if we use uniform pricing scheme. Then we learned about Lagrangian function, KKT conditions, and then we saw how we can use KKT conditions to verify if the market clearing price is correct. So if, for example, you can ask your code in Julia or Python to give you the dual variable of the power balance equality. Let's say it's 20. But now you need to verify it's correct. Then you can use KKT conditions analytically to make sure that price is indeed the market clearing price. So it's part of your step 1 of the assignment 1. Is it clear? Good. Then in your assignment 1, there's step number 2, where you extend what you learned in the previous lecture to have multiple hours. So what I taught you last lecture was for only 1 hour. But what if we have 24 hours? So can we simply run what we learned 24 times separately? So why is multi-hour problem is our concern? Or is it our concern? Is my question clear? So last lecture, you learned that how you can clear market as an optimization problem for 1 hour. Step 2 of assignment 1 says, okay, extend it for 24 hours. Is there any element in that task, in that step, that avoids you to run your optimization problem 24 times separately? Yes? The battery. Battery has constraints that link hours. It's called intertemporal constraints. So then you cannot run the market for every hour separately. You have to run the market for all 24 hours together. Clear? You can think of many assets that have has intertemporal constraints. For example, in battery, the energy you have in the battery, it depends on what the energy stored level from the previous hour and what charging, discharging you have in the current hour. But can you think of any other assets that has intertemporal constraints? Conventional units, what kind of intertemporal connectivity they have? For example, ramp rate. For example, if you have a coal unit, you cannot increase or decrease the production level more than a certain level, like 50 megawatt. So you say my production in this hour minus my production the previous hour cannot go beyond 50 megawatt. Is it clear? So I'll leave the step 2 of assignment 1 to your own, curiosity to explore it. But now let's go for the new lecture. And based on what you learned today, you will be able to solve step 3 of your assignment 1. Deal? Good. And still, people online, you are more than welcome to write your questions. Or if I ask any question, you can write the answers in the chat box. I check it very often. Good. Again, remember, in Europe, we have a zonal setup. We have this map showing different bidding zones in Europe. Also, we had this slide from the last lecture, the 4 different markets. We see that, okay, in terms of the time, first it's ancillary service markets. It's in green. It's the TSO, Energinet in Denmark, who runs that. Then day-ahead market and intraday markets. It's the market operator, Nord Pool, who clears that. And then we have balancing market. Again, it's green. It's the TSO. So in different lectures, we are going to talk about different boxes. But today, it's only about day-ahead market. Clear? Very good. So hopefully, at 3:30 today, in 2 hours, you will be able to explain the fundamentals of day-ahead market. You will be able to describe the concept of something called day-ahead market coupling in Europe, analyze the network effect in the market clearing problem, formulate as an optimization problem both nodal and zonal market clearing problems. It's exactly the task 3 or step 3 of your assignment 1. And then we will not go in deep, but I like to explain you what is the concept of flow-based market coupling. It's something that now the Nordic started implementing that since last November. So I like to give you the idea. It's something that improves the zonal setup. It doesn't make it as efficient as nodal, but something in between. Okay? We are going to talk about that. So, outline, only 6 items, easy. So, fundamentals of day-ahead market, single day-ahead coupling stack in Europe, network effects, power flow equations. Power flow equations will be like reminding. Hopefully, you had some courses in past on power flow equations. If not, again, I'll try to give you a preliminary, let's say, description. Then market clearing optimization problem, nodal versus zonal. This is exactly what you need for step 3 of your assignment. And finally, a brief description of flow-based market coupling in Europe. Any question? Do we have a clear idea what you expect in the next 2 hours? Very good. Good. Fundamentals. Day-ahead market in Nord Pool, or in Nordics if you want. So what does this figure show? Check it for a minute. So what we do is that in day D minus 1, on that day, until noon, if you are a producer or if you are a consumer, you submit your offers, if you are a generator, if you're a producer, or your bids, if you are a demand, if you are a retailer, to the Nord Pool or, to the day-ahead market. Then there is a time window of maximum 2 hours for market operator to clear the market, to solve an optimization problem, and disseminate market outcomes. What are the market outcomes? The market outcomes are prices and quantities for production and consumption for every hour of the next day, for hour D. Is it clear? So just to make sure that everything is super clear, let's go to the Nord Pool website together. Just see that, yes, what we are saying is there. So this is Nord Pool website. So you can go here, the item called market data. If you go there, there are a lot of information, including day-ahead market. There are also other markets that we are going to talk about in the future lectures. But let's stick to day-ahead market. For example, here, we are in prices section. So, for example, it's already DK2. What is the date? It's for tomorrow, 18th of February. And then you can see the price in different hours in DK2. We can come, for example, for today, the current hour. The price is quite low. It's about 106.78 euro per megawatt hour. So you see that we have hourly time resolution. There are more things that we are going to discuss soon in this lecture. But for example, in the first lecture, I showed you this aggregate bidding curves. For every hour, you can see the demand and supply curve for every hour of the day-ahead market in every bidding zone. Actually, you can also go here. There are map function. And for example, today, this is the average price. But let's go for a specific hour. For example, the current hour, 13 to 14. Yes, and prices in euro. And you can see the prices. Is it clear? And you can play with prices. For example, go to the next hour. You see that prices are changing in different bidding zones. Clear? So you can play with this data later. Let's get back to our presentation. So last time I told you something that I need to correct it. I told you that I'm not sure when Nord Pool or European day-ahead markets will change to 15 minutes. But actually, I can correct it that it will happen very soon. In June 11, 2025, in 4 months, all European day-ahead markets, they will change granularity, or a market term called market time unit, MTU. It will be changed from 1 hour to 15 minutes. Is it clear? So we are going to have 1 day-ahead price per every 15 minutes, not per hour anymore. Do you think it's good or not? It's good to have a better, finer granularity, like 15 minutes. Why do you think European markets took that initiative to go from hour to 15 minutes? So now, instead of having 24 time intervals, when you solve optimization problem, you are going to have 24 times 4, which is 96, right? So your optimization problem will be more complex. But why do you think it's good that they did that? Any reflection?
price will be lower, I guess.
The price will be lower.
I guess, what do you think?
Since the price is lower, so we reduce the market granularity. Think of technologies. Yes, please.
With higher granularity, you can manage your reserves better, and then
You can manage what?
your reserves.
Your reserve. It's a day-ahead market. Reserve market is separate, right? Actually, reserve market will also be 15 minutes, but it's not the discussion at the moment. Raul?
Maybe due to relying more in renewables.
Yes, renewables plays a factor. But why for renewables it's interesting to go for 15 minutes?
Forecasts are now better.
Yes. If you have a wind power or solar, your forecast, if when you forecast, okay, in a certain hour, my production will be X megawatt. Will it be exactly X megawatt during that hour? If it becomes 15 minutes, you can have a better forecast, right? So maybe you can say, the first 15 minutes, it will be X megawatt. In the next 15 minutes, it will be, I don't know, X plus 5 megawatt. That's one reason. Very good. That's the main reason, actually. Can you think of any other reason? Is there any asset that we like them to have in the market? And if we have 15 minutes rather than 1 hour commitments for them, we can have more participation from them. It's part of your assignment, actually. Batteries, right? Batteries. If batteries, they see that, okay, they will have commitment for 15 minutes rather than 1 hour, it's more likely that they will be more active in market participation. Good. So I'm very curious to see that how prices will evolve by changing MTU to 15 minutes. Yes, please.
In the short term, will this benefit the generators that are able to ramp up their production really, and they have high values?
Okay, that's a good question. There are some generators like gas that they can ramp very highly. Is it better for them? Likely. But remember, we don't have ramp limits in the market. It's part of their bids, right? Likely they can, yeah. I don't have a right away answer for you. It might be. Good. So, day ahead market. A market to be cleared a day before. Why? Why not hour ahead? Why not week ahead? Why not year ahead? Oh, okay, we have futures market. Yes, I know. But why day ahead? Have you thought of that? Who said day ahead? Why not 2 days before? Why not half a day before? Any idea? Yes?
For sure, some dispatch generators need to account for the startup time.
Exactly. So let's say back in time when we didn't have much renewables, like 20 years ago. Remember, electricity markets have been started operating from 1990. That time there was not much renewables. The most source of generation was conventionals, like coal, nuclear, I don't know, this kind of conventional generators. They are not super fast, especially nuclear, very slow. You cannot check. You have to tell them a day before, sometimes a week before, how their schedule will be. You cannot ask them, okay, for the next 5 minutes, change your schedule. They can't. Due to some thermodynamic constraints, they can't. The same goes for other conventional generators, especially coal. So a day-ahead market has been proposed that time to inform them a day before how their schedule will be for the next day. Okay? So at that time they thought, okay, a day before, it's good enough time for them, for inform them in advance how their schedule will be. But on top of that, there's also another reason. There is an economic reason. Okay, I'll not discuss that in deep, just for like a teaser to inform you. There are also some economic reasons. If you have economics background, It might be easy for you to read this nice paper from 1993. I did it when I was a PhD student, though I'm not economist at all. They show that if there is a market to be cleared before, we call it forward market or financial market. It doesn't matter, it's a day before, 2 days before, a year before, it doesn't matter. It just says that if you have a financial market, a forward market, it improves competitiveness of the market. So I'm going to use a jargon word now. That market reduces the market power of market participants. That's the only time I'm going to use this word, market power. Do you know what is that? Just for your general knowledge. Market power means some generators, they bid, they submit their offer price at a price higher than their true cost, and they know that still it will be accepted. And by that, they increase market price to their own benefit. We call it that generator has market power. And that offer is strategic. It's higher than the true cost. Good. So this study shows that a market to be cleared, a financial market to be cleared in advance, it reduces, not disappears, it reduces the market power of producers, or in general, market participants. Good. So these two reasons hand in hand, they are good reasons to have a market to be cleared in advance, close to real time. And here when I say close to real time, stay ahead, close to real time in comparison to a market to be cleared a year before. Okay, a challenge for you. Imagine in some years, hopefully, for example, in Denmark, in Nordics, there will be power systems 100% based on renewables. Wind, hydro, solar, blah, blah. Imagine we will have massive integration of distributed energy resources, like a lot of electric vehicles, storage, maybe electrolyzers, blah, blah, blah. There is no coal unit. There is no nuclear. There is no gas. And then the true cost, operational cost of these generators are zero or close to zero. All of them are fast enough. So we don't really need to inform them their schedule a day before. Even if we tell them, I don't know, 10 minutes, 1 hour before, it should be fine. So do you think the structure of the market we have, especially with day-ahead market, do we need to keep them in future? Any reflection? I'm not sure there is a clear answer, to be honest, but it's a very hot topic, I would say, open question. But most likely, no, we don't need maybe. But I just told you, imagine that everyone is bidding at zero price because everyone is renewable in future. Does it mean that the market price will be always zero? So why don't we clear the market if the market price will be always zero or sometimes even negative? And then, I mean, us consumers will be very happy, right? But all the power generation companies, they will disappear. They are not there for selling power at price zero. So just I'm trying to trigger you to think. Again, I don't think there is a clear answer today. But maybe in future, energy market should be seen as a service market. Can you give me a market that is based on a service? You consume it, but you pay based on the capacity. Can you give me an example?
Mobile phones.
Mobile phones. Exactly. For example, internet services or the bandwidth for mobile. You buy a capacity. You say, okay, I buy from different, there are different internet service providers, ISPs. You decide to buy from one of them. They give you a certain amount of capacity. You may use it, you may not. But you are not charged based on how much you consume, as long as you are consuming in that range. Maybe in future power markets will be exactly like that. Who knows? So if you like to do a good PhD, that's an interesting topic. Good. Single day ahead market coupling stack in Europe. Have you heard of that before? How many of you heard of stack? No, one. Okay, many of you will learn new things today. So stack stands for single day ahead coupling. All the text I will show you in the coming slides, it's borrowed from ENZOI. Remember, it's the Union of Transmission System Operators in Europe. And stack was launched in February 2014, though since then it has been changed a lot. Simply, it means that instead of every single country clearing its own day-ahead market separately, or every region clearing, like Nordic, clearing its market separately, let's have one market for the whole Europe. One market, one day-ahead market for the whole Europe, or most of the Europe. You will see the blue countries here who are part of stack. Do you think it's a good idea or not? Is it a good idea to, for example, clear day-ahead market in different 5 regions separately? Or having all of them in one market? Which one makes more sense? Yeah, please.
Difficulties when you have such a great zone of production one side and consumption on the other.
Yes.
So having smaller zones where it's more condensed, it's more efficient in terms of transmission.
Okay. So what's your answer? Is it better to go for 5 separate markets or one market?
Well, clear answer hard, but it has advantages and has disadvantages because you have more similar price.
Okay.
But maybe more.
Think of optimal resource allocation. It's not just necessarily for power, for any asset. Let's say that this part of the class, they trade, I don't know, something. It doesn't need to be power, anything, together between themselves. This part of the class and that part of the class. So we have 3 different markets. And you don't talk to each other. Each of them, they have your own market. Do you prefer that for the sake of society? Or do you have a one market for all of us? So then you can trade power, you can buy power from the other side of the class. Is it clear? So which one is more efficient? One market. There might be a case that here power is scarce, so then the price is very high. Power, energy is a very scarce commodity. At the same time, there might be in this part of the class, there are a lot of energy resources. So if we clear the market all at the same time, then the people in this side will have a chance to buy from this side. Otherwise, we are limiting them. They will not be able to see the other side. Is it clear? So always in terms of the resource, yes, of course, it brings complexity. I agree. But in terms of resource allocation, it's always better to have one market for everything. Are you convinced? Good. So stack is doing that. So there is a single pan-European cross-zonal day-ahead electricity market. Stack, I'm going to the last sentence, simultaneously take into account cross-border transmission constraints. So what is the constraint between the countries or regions? And by that, maximizing social welfare. Still, we are maximizing social welfare by clearing the market for the all Europe. Is it clear? A very tricky question to you. Here we are maximizing social welfare for entire Europe. Does it necessarily mean that we maximize also social welfare for every single bidding zone? No. That's the tricky part. We are maximizing social welfare for the whole Europe. It doesn't mean necessarily we optimize social welfare for every single bidding zone. But for the whole society, it's good. So they say that integrated day-ahead market increases overall efficiency of the market, promoting effective competition, increasing liquidity. Liquidity means that we have now more competition. So now people here, they can buy power from there or from here or from here. It adds liquidity. And enables a more efficient utilization of generation resources across Europe. I'll be back. So imagine, for example, wind power in Denmark is not producing much, while at the same time in Spain we have a lot of solar power. So then it's good to have one market, or other way around. There was a question? Yeah.
Just like when you said that the social welfare won't be optimized everywhere, wouldn't that mean that like certain places will consistently be having lower social welfare than the other ones?
Yes. If you that's a games theoretic question. I don't like to go in there, but sometimes you don't need to pick the best solution. You pick the second best solution. That while you are maximizing social welfare for everywhere, you also make sure that the social welfare in every zone is also the maximum. So you're trying to find the second best solution. It goes to the games theory domain. Okay? Good. So again, borrowed from that website. This is involved parties, TSOs, including Energinet. You can see there. Energinet is somewhere, yeah, in the second line. And also NEMOs, nominated electricity market operators, including IPEX and Nord Pool. So all of them, they are in the same plate running a stack, a single market for Europe. I'd like to give you some statistics, and then we'll ask a challenging question, or maybe you will ask first that question to me. Almost 99% of EU consumption from day-ahead market is coupled. 1,530 terawatt hour per year is the trade in that market. In terms of the financial value, 200 million euro daily. And the complexity. The optimization problem to solve day-ahead market for all Europe with 1 hour granularity today is 17 minutes. So it's not that complex. So, but remember, different countries, different bidding zones, Nord Pool, Apex, they may have different regulations, blah, blah. So yes, all TSOs, all NEMOs, market operators, they come to the same platform, but there should be a union algorithm to clear all markets. And that joint algorithm is called Euphemia. So Euphemia is an algorithm that every different market operators, Nord Pool, Apex, blah, blah, they bring bits. Then there is a single optimization to be solved. And this optimization problem is following an algorithm called Euphemia. It's almost the same as what you learned, social welfare maximization, linear. The only difference is that also you include block orders. You remember we discussed about block orders, right? The last lecture. So I will not go in depth of Euphemia, but it's almost what you learned so far. Euphemia, or also PCR Euphemia, price coupling of regions. So let's check the third bullet point. Input data to Euphemia are network capacities. Who provides network capacities and constraints? It's TSOs. So TSOs provide input data about the capacity between bidding zones, and the bids and offers provided by NEMOs. Also Nord Pool, Apex, others, they bring the bids they collected. That's the input data. Then Euphemia clears the market, matches energy demand and supply for the next 24 hours for the entire Europe. The process maximizes social welfare, so it's not different, social welfare for the entire Europe. Outputs are clearing prices, matches trades, so how much quantities to produce and consume, scheduled exchanges between countries, between bidding zones, and the position of bidding areas. So as you see, it's the same as what you learned before, just it's in the European level. So I have, let me see if it's the right time for asking that question. Yes, it is. So there's one market, one day-ahead market in Europe. But I told you so far, Nord Pool is a market operator. Apex is a market operator. I don't know, OMI in Spain is a market operator. But I'm telling you there's only one market. Is Nord Pool a market operator? So what's your answer?
Constraints in the transmission network, the connectivity. There's constraints in the connectivity.
But that's, yeah.
So you have to operate the market separate, even though...
No, there's only one market. Let me find the chart. What this page says is that there is a stack which is running based on Euphemia. TSOs gives us data of, we will call it later NTCs, net transfer capacities among zones. So how much we can trade between zones. This is TSOs provide. NEMOs means nominal electricity market operators like Nord Pool. They provide collected bids and offers. There is one market clearing. You are maximizing social welfare, and now this is market clearing outcomes. Market clearing outcomes. So there's one market, not 10 markets, one market. So I'm asking you, Nemo, Nord Pool, is it the one who clears the market for Nordics? Or it's Euphemia who clears the market for all Europe, including Nordics? Is the question clear? The answer is that, in reality, we say Nord Pool is market operator, but if you really want, Nord Pool is a bid offer collectors. Apex, others, they are collectors. They come and put all the bids offers in the same plate. And then NEMOs together, they clear the market. So when we say the market is cleared, it's not just Nord Pool. All of them together under Euphemia clear the market. But there's only one single optimization to solve. It's not like one optimization in Nordics, one optimization in Germany to be solved. No, one optimization. Is it clear? Good. Well, let's, now we learned about a stack. So I showed you market clearing outcomes from Nord Pool website. Still now you can see it in my slides. These are stack market clearing outcome results, the stack market clearing results. So that's why, for example, if you have a generation asset in Nordics, you can choose where to submit your offer in Nord Pool or Apex, because all of them, they are collectors, and eventually they will bring your bid, your offer to stack, right? So these are the stack market clearing outcomes. If you go and check, for example, Apex Market, the Apex website, you will see the same outcomes. The market clearing outcomes are the same in all websites, because all are coming from stack. Clear? I hope. Good. So this is you can see the market clearing outcomes the day ahead for today, for previous hour. And the first things you see here is this number, SYS, SYS, it's system price, and it's 102.32 euro per megawatt hour. Do you know what that price is? It's the market clearing price assuming no transmission grid constraints. If we had copper plate system, it's exactly like step 1 and 2 in your assignment. There is no transmission constraint. We assume that the system is copper plate. You can transfer power from any point to another point. If we had that hypothetical system, then the price was 102. Is it clear? But now let's see the real prices in different bidding zones. For example, in Germany, it's 106, while in SE2, it's 40. Some higher, some lower than system price. So for example, in the red box, you will see that in this specific hour, the price, day-ahead price in Germany, DK1, also DK2, if you zoom in, you will see the same price. And SE4, the fourth bidding zone in Sweden, they are all the same. While in the purple box, including different bidding zones in Sweden, SE2, SE3, and 5 bidding zones, or here in this box, 4 bidding zones of Norway, they are all different. While SE2 price is 40 euro per megawatt hour, I don't know, in Norway too is almost 100 euro per megawatt hour. So different zonal prices in purple and identical zonal prices in red box. Why? Why do we see different prices? Some zones have identical price, some have different prices. Why? What is the reason? Yes?
Two zones are next to each other and the transmission lines are close, they become more...
Exactly. The reason is transmission, grid constraints. So that's why now you are going to learn about network effect on market clearing outcomes. So for the next 1 hour, or maybe even longer than an hour, we are going to learn about how to include network constraints in market clearing problem, optimization problem, and how this constraint form various prices for different zones. Clear? So hopefully, after today, we will understand why this is happening. By the way, we will have, again, a Kahoot exam quiz with 16 questions again. So please listen carefully. Still, you will have that 1% reward. Network effect. Let's start again from a very simple illustrative example. Please check the example. 2 buses. Bus 1, bus 2, connected one by a single transmission line. G1 and W1 connected to bus 1, G2 and demand connected to bus 2. Demand is bidding, so it's elastic to price. So we are going to maximize social welfare because we have elastic demand. And just to clarify, I'm going to use the terms bus and node interchangeably. So they are the same things. So bus is more power system term, while node is more for graph theory or something like that. So, but they are the same. Yeah, we use them interchangeably. Good. Imagine the capacity of transmission line is 80 megawatt. So you can transfer 80 megawatt maximum from one side to another. It could be from bus 1 to bus 2 or from bus 2 to bus 1. Here, since the only demand is in bus 2, so obviously the power flow will be from bus 1 to bus 2. But if you have a meshed system, you cannot forecast. It might be not trivial to know in advance what the direction of flow will be. But here it's obvious, right? From bus 1 to bus 2. Okay. If the transmission line capacity is 80, what will be the production level of W1, G1, G2? W1, 20, because it's the cheapest. Then G1, 50, because it's the second cheapest. So 50 and 20 together, it's 70. 70 megawatt you are transferring from bus 1 to bus 2. Is it possible? Yes. So how much, what's the schedule of G2? 20. And demand is fully supplied because demand is buying at price 40, higher than the bid of offer price of any other generator. So power flow from bus 1 to bus 2, 70. Okay, what are the market clearing prices at bus 1 and bus 2? The same, which is 30 euro per megawatt hour. If I remove transmission line and assume that all these 4 elements, 3 generators and 1 demand, they are all in the same location, copper plate, will it impact the market clearing outcomes? No, because transmission line constraint is not binding. Transmission line constraint is not active. We want 70 megawatt to transfer while the capacity is 80. Okay, the market price in both nodes, both buses are the same, which is 30. Why 30? How to know that in both buses the price is 30? How can you check it? Of course, by KKTs you can check it. You learn how to verify it. But intuitively, how can you check it? Yeah, the last generator here, yes, it's 30. But how do you know the price in bus 1? So intuitively, add a single demand in every bus that you are looking for and check by adding a demand, for example, 1 megawatt demand in that specific bus, how much your objective function here, social welfare, is changing. So if you add 1 megawatt in bus 2, so for example, the consumption goes to 91 or reduces by 1 megawatt, from 90 goes to 89. Which generator will have a different dispatch? You are only playing with the dispatch of G2. And what's the offer price of G2? 30. So the price at bus 2 is 30. How to know about bus 1? I can assume that there is 1 megawatt demander. 1 megawatt demander in bus 1. Who is going to produce that? Still G2. Still G2 is the one who will provide extra if there is 1 megawatt demand in bus 1. Is it clear? So in both cases, in both buses, the price is 30. Okay. What is the payment to W1? How to calculate the payment to the W1? What is the price? 30. How much it produces? 20. 30 times 20, 600. So the 3 generators, W1, G1, G2, they are being paid at price 30, while demand is charged at price 30. Do you agree? Okay, and in this case, we have budget balance. What does it mean? As a market operator, you collect payment from the demand. Sorry, you collect the payment from the demand, which is 2,700. And you pay to the 3 generators, which is 600 plus 1,500 plus 600. It adds up to 2,700. So what you collect, you pay to generators. Budget balance. Is it clear? Okay. What should be the next slide? What should we do now? Reduce the capacity. Now it's 60 megawatt. Is the transmission capacity, the constraint of transmission capacity binding? It is binding. So give me these answers. Production level of W1. How much? 20. What about G1? 40. Is it full dispatch at full capacity? No. What about G2? 40. But you remember, I told you that in the first lecture, we have something called the merit order in the supply side. So first, we schedule the cheapest and then the second cheapest. But here, we are violating merit order. Though, sorry, although G1 is cheaper, but we are not fully dispatched G1 and dispatch more G2. So transmission line capacities are one of the reasons that we may violate merit order. Is it clear? That's why it brings inefficiency, because we didn't use the full capacity of a cheaper generator. Anyway, so what is the power flow from bus 1 to bus 2? 60. Good. Tell me the market clearing price at 2 buses. Bus 1, bus 2. Let's start with bus 2. It's maybe easier. What's the price in bus 2? 30. Why? If you increase the demand there to become 91, who is going to produce that 1 megawatt? G2. Price is 30. Bus 1? 20. Why?
Decrease again.
If we have 1 megawatt demand there, it's G1 who is going to produce that. So the price there is 20. And if you solve the optimization problem, you will see that. Also, you can verify it through your KKTs. So why different prices? As we just said, if by any 1 megawatt change in demand at bus 1 causes a 20 euro change in social welfare, while that change at bus 2 results in 30 euro change. Is it clear to everyone? Actually, this is part of your step 3 of your assignment. Okay, payment to W1, G1, G2, D1. How much we are going to pay to W1? What's the price at that node? We pay people at the price in the node they are located. So what is the price at the node of W1? 20. How much wind is producing? 20. So we are going to pay 400 euros to W1. Is it clear? How much we are going to produce to G1? Again, the price is 20. You're right? Is it correct? While it produces 40 megawatt, we are going to pay 800 euro to G1. How much we are going to pay? V means market operator. We are going to pay to G2. What is the price at the node G2 is located? 30. How much does it produce? 30, right? 30. Like 60 comes from there, you have 90, so 30. So we are going to pay 900 euro to G2. Good. How much we are going to charge demand? It consumes 90. At what price? 30. We are going to send a bill of 2,700 euro to the demand. How much we are going to pay to 3 generators? €2,100. Now compare these two. As a market operator, you collect 2,700, you pay 2,100. There is a surplus of what? Surplus of 600 euro. What's that? Are we earning money? What's that? Social welfare? Oh, don't say that, please. What's that? Any idea? Yes.
Congestion paid to this one.
Yes. How do you know that? Did you have any other course? Pardon me? Okay. Yes, it's called something called congestion rent. That's a new term you'll learn. Congestion rent. Or also some people, they call it congestion revenue. What is that? We saw that bus one, right? Yes. The price is 20 euro per megawatt hour, while in bus 2, the price is 30 euro per megawatt hour. And what is the flow? 60 megawatts, right? This is what the market clearing outcome is, right? Imagine that you are a trader, trader between countries. We call it a special arbitrager. Arbitrage over spaces, over space. Imagine you buy 600 megawatt at price 20, transfer it, sell it at price 30 at bus 2. Like many other traders, you may buy something from Spain, I don't know, some vegetables, and bring with ships and sell it in Denmark. It's like that, right? Special arbitrager. So if you do that, how much you will earn? You sell 60 megawatt, you are going to sell it at price 30, but you already paid at price 20, which is 600 euro. It's the same as this. Is it clear? So that 600 is that. It's congestion rent. Buying power from one point, sell it at different point. If the prices are different, you will earn. If the prices are identical, you will earn nothing. Are you following me? Good. So at least now we know what 600 euro is. It's congestion rent. But who is getting that money? Who is getting that money? That's the question. Now, market operator should pay 600 euro to someone. Who is that someone? Any idea? Yes. In general, grid owner. Grid owner is the one who earns that money. In our case, it's TSO. Transmission system operator earns 600 euro. So, this surplus belongs to the grid owner, here TSO. One can think of grid owner as a special arbitrager, buying 60 megawatt of power at bus 1 at lower price of 20, transferring it to bus 2, and sell it at a higher price of 30. This is similar to storage. Storage does arbitrage between hours. It's temporal arbitrager, while here grid owner is a spatial arbitrager, buying from one place, selling it at a different place. Yes?
But doesn't that incentivize the TSO to have less capacity than it needs to have? Like,
this is my question to you. What you are asking exactly. Can you ask the question loudly to the class?
If the transmission system operator is being paid when he can't deliver the power which is needed to flow over his lines, he can save money building lines and still getting paid because it can't flow over them.
Very good. So let me reword the question. That's a question of me to you, and also his question. What's your name?
Niklas.
Niklas' question to you. So Niklas says that if in the previous example, when the transmission line capacity was 80, how much congestion rent was in that case? Remember, if it was 80 and the price is 30, what is the congestion rent? 0. Okay, grid owner has a bigger asset or asset with a higher capacity, earns 0. In a different case, grid owner has a tighter capacity, 60 megawatt, and earns $600 or euros. Does it mean that grid owner is incentivized to create congestion? Is it? Is the question clear? And answer?
Yes.
Yes. Yes. And that's why market regulator is there. Market regulator says, yes, okay, you can get that money, okay, but you should not plan for that. So, yes, the TSOs, for example, if this is Denmark, this is Sweden, there are 2 TSOs involved. They split the money between them. So 300 euros goes there, 300 euros goes there. But they are not allowed to put it in the pocket. They put it in a separate pocket and use it the same pocket that, I don't know, grid tariffs, other incomes of TSO goes there. And they should use that money for grid expansion. It's the regulation. Otherwise, yes, TSO is for profit. Unless a regulation comes. Is it clear? For example, maybe you heard that Energy Island in Bornholm, Baltic Energy Island, is going to be a 3rd bidding zone in Denmark, right? DK3. DK3. Okay, now it's being recorded, so I'm saying anyway. So they're going to be DK1 and DK2, and then system operator is responsible to create a line between Bornholm and DK2. Some developers, they want to come and invest here, like wind farms, whatever, in Bornholm Island. But they don't do that. They are arguing with Energinet saying that we are going to invest here if you provide us something called transmission access guarantee, TAC. If you don't provide us TAC, we are not going to invest here. It's one of the hot topics today in Denmark. So why do you think investors here want transmission access guarantee? Yeah, Raul?
You get paid by the price of DK2.
Yes. Let me help you. If the capacity of this line is not that high, if a lot of investors come and invest a lot of offshore wind farms here, what the market, and there is not much demand here, it's a small island, the power is going to be transferred to other parts, to DK2 and then to Europe. So if the line is congested, what the price will be here most likely? 0. And the price here will be something high, I don't know, for example, 50 euro. We are going to pay investors at price 0. Who is going to earn all the profit? Energinet. Congestion rent. So that's why investors say that we want TAC. If we want to make sure that always we will have, for example, a guarantee of X megawatt to have access to the transmission line. Otherwise, we are not going to invest here. Is it clear? Good. That could be a good master thesis for you, by the way. Good. We are very late. Let's move on. So what we learn is that uniform pricing is budget balance because total payment to W1, G1, G2 plus the congestion rent all together is equal to the payment to the demand. Payment of the demand. So demand pays 2,700, 600 goes to TSO, 2,100 goes to 3 generators. It is budget balance still. Good. Market clearing as an optimization. Can you check it for a minute? How did we change the optimization problem for market clearing, including transmission capacity? What do you see as a change with respect to the model we had in the previous lecture? Anyone? Do you notice any change? Yeah, please.
The generation demand equations kind of split up both buses.
Yes. Yes. The last two constraints. Okay, now we have a new variable, power from bus 1 to bus 2. The optimization problem, social welfare maximization remained unchanged. Then we have this new constraint saying that power from bus 1 to bus 2 is between 60 and minus 60 because the capacity of the line is 60. So the upper bound is 60. The lower bound is not 0. It's minus 60. Why? Yes? Because it can go two ways. Here in this example, it was trivial that the flow is from bus 1 to bus 2. But in many cases, it's not trivial. If, for example, it's a meshed system, like a triangle, it's not clear, it's not obvious, then you make it between 60 and minus 60. It becomes minus. What does it mean? It means that it's in the other direction as what you supposed. And what are the last two constraints? We have power balance equality, one for each bus. Can you tell me, for example, in bus 1, can you tell me about the signs? Why the first term is positive, the sign behind, while for W1, G1 is negative? So it was like here, right? For bus 1, it was like this. Generator G1, wind, and this is the flow from bus 1 to bus 2. So this looks like a demand. Total production equal to the total demand. And for bus 2, it's like P from 1 to 2 is like a generator. Also, you have G2 generator, and you have a demand. So the P1 to 2, the power flow, plus the production of G2 is equal to the demand. And of course, here we assume that the flow is from bus 1 to bus 2. If it is wrong, the optimal solution will be negative. It means that it's in the opposite direction. So the key is that now we have two dual variables. So then we have two. So that's why, for example, the price in one bus is 20, the other is 30. You ask Python code, Julia code to give you dual variable of power balance equality in every node. One will be 20, the other will be 30. Is it clear? Good. Power flow equations. Here you assume that you order electrons like a king, saying that go from bus 1 to bus 2. Is it the case? Remember, the power flow, the transmission lines, the transmission network is something like this. It's meshed. And the power flow in an electrical transmission network is governed by the laws of physics. And when I say laws of physics, I'm talking about Kirchhoff's and Ohm's laws, right? I used to teach general electrical engineering course, teaching AC power flow. how many of you learn about, you know about what AC power flow is? Do you know? Okay, more people in this line knows? Okay, good. Okay, let's have. So in fact, it's AC power. AC stands for alternating current. AC power flow equations are used to calculate the amount of power to be transferred across each transmission line. You cannot say that, okay, the market outcome is 60 megawatt. 60 megawatts electrons should go from here to here. No, it's the laws of physics. So almost half of the class knows about AC power flow. Let's have a very quick recap, but if not, I used to teach this book to my bachelor students from Alexandra von Meyer. It's a good book if you want. But I'll tell you about. Have you seen these equations at all in your courses? It looks ugly, right? But it's not complicated. No, it's not scary. Have you seen them? They call it AC power flow equations. If you are a power engineer, it's like the most important equations for you. Let me tell you, I don't want to scare you if it's the first time you see this, but just to tell you. So imagine I is index for bus. For example, you have, I don't know how many buses, 10 or whatever. In the previous example, you had 2 buses. So I is bus. K is also a buses. For example, K1 to N means buses connected to bus I. PI is active power in megawatt. QI is reactive power in megawatt. Do you know what reactive power is? It's a power being alternating between demand and source. Well, it's a market course. I'm not going to teach that, but, well, reactive power. These capital V's are voltage magnitudes. Thetas are voltage angles in radian. G and B are network characteristics. They are input data. G shows conductance and B shows susceptance. You saw the word susceptance in your assignment. So for every bus, depending what type of the bus is, out of this, we have 4 characteristics, P, Q, V, and theta. P active power, Q reactive power, V voltage magnitude, theta voltage angle. So for every bus, usually we have 2, and solve power flow equations to calculate the other 2. Do you know how we can solve power flow equations? Have you learned that? Are you remember the names of the methods to solve power flow equations? Newton-Raphson, for example. They are numerical methods. And if you put these ugly equations in any optimization problem, why I'm talking about this? Because I like to bring these constraints to my market clearing optimization problem. Because my market clearing optimization problem should be aware how electrons are flowing. I cannot order them. So market should be aware how electrons travel from one point to another. So I want to put this constraint in my optimization problem. But the problem is that these constraints are nonlinear, non-convex. Ooh, new terms. Why they are nonlinear? You see multiplications of variables like the Vi times Vk. Also, you see nonlinear operators like sine and cosine. If I put them in my optimization problem, it will be non-convex. Do you know what non-convex optimization is? Have you heard of that? For example, if you have an optimization problem saying that, easy, maximize x, x is between 0 and 2, sorry, x plus y, and y is between, I don't know, 0 and 4. The solution is obvious, right? X equal to 2, y equal to 4 is the optimal solution. But if you draw the feasible space is that this is x, this is y. Y can be between 0 and 4. X could be between 0 and 2. So this is your feasible space. So your solution can lie at any point here in the feasible space, and particularly your optimal solution is here. So your optimal solution is part of the feasible space. Is the solution here optimal? No. Is it feasible? Yes. Is this point? Is the solution feasible? No. Clear? This optimization problem is convex. It means that if you pick any two random points within the feasible space, if you connect them, it will not go beyond feasible space. The line will stay in the feasible space. We call it convex. Is it clear? What about this? Is this feasible space convex? No, because if you pick, for example, these two, then here you are going beyond feasible space. It's non-convex. Why is it important to talk about convex and non-convex? For convex optimization problems, if you solve the optimization problem and get the solution, optimal solution, you can say for sure, I guarantee my solution is optimal solution. But for non-convex problem, you can solve it. You will get a solution. That solution is definitely feasible, but not necessarily optimal, global optimal solution. For example, your feasible space could be something like this. You are trying to find this point, but you end up to this point. We call it a stationary point, local optimal. So you reach out here, you say, I found optimal solution. No, it is local optimal solution. The global is here. Good. So if I bring these ugly constraints to market clearing optimization problem, it will be non-convex. It means that I can solve it. Solution is feasible, not necessarily global optimal. Are you following me? So this is a nice figure from Ian Iskenza and his teams. They show for a 3-bus system, AC system, how feasible space looks like. Extremely non-convex. Good. So what I want to do is that I like to bring AC power flow equations. That's the reality. It comes from Kirchhoff's and Ohm's laws to my red box, the one that I have power flow constraint. Before naively, just I said power flow from this point to another should be 60. But in reality, the equations that govern power system is the blue ones. So shall I include them here? Do you suggest me to include blue box in the red box instead of power flow limits? If I do that, what will happen? My optimization problem will become non-convex. But remember, here we are solving day-ahead market. I'm not running the market. I'm not the TSO here operating the system in the real time. It's day-ahead market, a day before. You can see it as a financial market. The outcomes are like contracts, right? It will be traded tomorrow. It will be delivered tomorrow. You trade now, it will be delivered tomorrow. So let's do easy job. Have you heard of linearized AC power flow equations, DC OPF, DC power flow? Okay, now we like to slaughter AC power flow equations. This is your AC power flow equations. Let's do a nice approximation together. Have you seen it before, this kind of approximations? Voltage magnitudes, who cares? Let's say they are equal to one per unit. Yeah, remove them. GIK, conductance. In transmission lines, the impedance part is usually more than the resistance part. So let's remove it. Who cares about losses? Theta I minus theta K, the difference of voltage angles between buses I and K. The difference is close to 0. And then sine of something close to 0 is close to that thing. So let's replace sine of theta I minus K by theta I minus theta K. Reactive power, who cares? Let's say it's 0. You see how we slaughtered. It becomes this. It's called linearized power flow. B is susceptance, what I asked you in your assignment to put 500 for every line. Theta I minus K is the difference of voltage angles, but they are not the voltage angles anymore. They are just variables. We killed AC equations. But this is linear. Is it clear? Yeah, so now we only have P, theta, and B. B is the input data, susceptance. P and theta are variables. You're following me? If I solve an optimization problem based on these, the lower box, linearized, is the solution necessarily feasible in reality? Not at all. So there is a very good paper by Kyrie Baker, explains that solutions of TCOPF, DC is the one we got after approximation, are never AC feasible. But, well. Good, I put that there. You're following me? Yeah, someone poll said that as far as we know, euphemia is also non-convex due to block orders. Okay, that's true. When we say something is non-convex, either you have multiplication of variables or a non-convex operator like sine, cosine. If you have binary variable, also it's non-convex. Yeah, in my PhD course, I mean, still the video recordings are on YouTube. I explained that if you have binary variables, how you can clear the market and what are the challenges. So in both US markets and euphemia, we have binary. In US markets, we have binary of unit commitment constraints. The units are on or off. In euphemia, we have binary of block orders. In both cases, we have to deal with binaries, but how? I don't want to explain here. But easiest way is that you solve a problem with binaries. It's mixed integer linear. Then you find the optimal binaries. You fix it. Then you fix the binary variables to what you got. It's 0 or 1. It's linear problem. You solve that. Are you going to have challenges? Yes. You will have some pricing issues. But I'm not going to talk about that here. If you are interested, you can check my video recordings. Good. Yeah, that was a question on the chat box. Market clearing optimization, nodal versus zonal. So, yeah, we are a bit long today. So I hope you are still excited to learn. These are data I got it yesterday. So the one in the right-hand side is the zonal prices in euro per megawatt hour. In Europe, I got it from Nord Pool, February 17, 1 to 2 p.m., the last hour. So you'll see that we have one price per bidding zone, like one price for Germany. The other one, the left one, is nodal prices in dollars per megawatt hour in CAISO in California. It's for results for market outcomes for yesterday, 10 to 11 p.m., actually the time I was preparing slides. So you'll see the prices, nodal prices, at every different node in California. So it doesn't mean that in whole California you have only one or two prices. No. At different points, you may have different prices. In Europe, each bidding zone, like Germany, like DK1, has a single price. So one price for each bidding zone. So what we do, I think we discussed last time, we ignore the transmission lines inside the bidding zone. So whatever network exists inside Germany, we remove them when we clear the day-ahead market. Is it clear? I'm gonna modify this statement a bit later. But zonal market is that. You will see the whole DK2 as one single zone. You will see the whole entire Germany as a single zone. It means that whatever exists inside Germany, the networks you ignore. In terms of topology, in terms of transmission line capacities, everything. And just you simply say that, this is a new term, NTC, net transfer capacity, how much we can transfer between two bidding zones. Clear? So the second statement, we will modify it to some extent when I talk about flow-based coupling. In US, no, we say we model the network as it is. You have 10 buses, we put all the 10 buses in the market clearing problem. You have 15 lines, we put the transmission capacity line of all 15 lines in the market clearing optimization problem. So that's why you are going to have one price per node, nodal prices, or also it's called locational marginal prices, LMPs. So LMPs are nodal prices. So here in the hit bar, you can see that it's written LMP, which is between minus 150 and plus 150. Are you following me so far? Okay, I told you that in Germany, or in every bidding zone, but okay, I keep talking only about Germany here. When you clear the day-ahead market, you ignore all transmission lines inside Germany, in Germany, and clear the market. So the question is that, are these market clearing outcomes feasible for transmission lines in Germany? Are they necessarily feasible? Is question clear? So you ignore all the transmission lines in Germany when you clear the market. You drive market clearing outcomes. Are the solution of the market necessarily feasible for transmission lines in Germany or any other bidding? No. So that's why you need something called redispatch. So what happens is that when day-ahead market is done, or also intraday, TSO says, okay, you have 100 megawatt accepted bid in Germany or in DK2. Tell me what is your plan. You may say that, okay, 20 megawatt out of 100 will come from that generator. The other 80 will come from the other generator. The first generator is in Lungbu. The other one is in Copenhagen. Then TSO checks if this solution feasible. If not, TSO should do redispatch. What I can tell you is that today, German TSOs in particular, they incur significant annual redispatch costs in the order of multiple billion euros just for redispatch. Is it clear? What happens is that you are going to have one price for the whole Germany, for every bidding zone. Good. But then we should pay altogether a huge redispatch cost maybe. In Denmark, it's not huge at all. In Germany, it is. I don't know about other countries. To make the market clearing outcome feasible. In US, you don't do that much because you use Nodal system. The other things I like to tell you is that the different TSOs, they have to coordinate the NTCs, net transfer capacities, how much you can transfer from one zone to another. How to do that? Now in Europe, there are 6 agents called Regional Coordination Centers, in abbreviation RCC. The Nordic RCC is in Copenhagen. And they do a lot of some tasks, but one of the tasks is to coordinate between TSOs how much we can transfer from one zone to another. Is it clear? Good. So this is like a step. Hope it's fine that we go 20 minutes more. I hope you're fine. This is what you are going to do, for example, in task 3 or step 3 of your assignment. This is a nodal system if you pick 24 bus. So you have 24 buses and, I don't know, like 40 lines. If you go for zones, you are going to say all the nodes, for example, nodes 1 to 13, I put them in zone 1. And everyone in nodes, the rest of the zones, I put them in zone 2. So you're simplifying this network to this very simple network. The only things that you need to know is NTC between zone 1 and zone 2. And that's what TSOs or RCCs, they coordinate and tell the market what the NTC is before market clearing. Or you may have 3 zones. You may say, okay, all the nodes here, I put them in zone 1. All the nodes here, I put them in zone 2. All the nodes here, I put them in zone 3. So I have 3 NTCs to determine. NTCs are input data for zonal market clearing. Who determines NTCs? TSOs in coordination. Who does coordination? RCC, like Nordic RCC. Okay, linearized power flow. As we said, we are using the linearized power flow. It's linear, it's convex. So we know that if we solve the problem, optimization problem, the solution is globally optimal. We use this. We already saw how we got it from AC power flow equations. The power flow from bus N to bus M is susceptance of that line connecting bus N to M times the difference of theta, voltage angle, at bus N minus bus M. That gives you how much power is going from bus N to M. Is it the true one? No, it's approximated one. Remember how much approximations we had. We slaughtered the AC power flow equations to get it. Why? Because it's linear. And then also we say that power flow between buses N to M is between F and minus F. Why minus? Because if it takes the opposite direction. So, the compact form of market, this is exactly what you are going to solve in step 3 of your assignment. This is the nodal optimization problem for market clearing. Can you check it for a minute to see how it looks like? Or what is that? Okay, can you explain me, one of you? What do you see new? This is exactly what you are going to solve as part of step 3 of assignment 1. Let's go one by one. Set of primal variables. PG is the generation of G, generator G. PD is the demand of consumption of demand D. Theta N, it's voltage angle of bus N. Social welfare, is it the same as before? Do you see any change there because of adding network? No, it's still as it was. The first 2 constraints, you already had them. The consumption limits of demands and production limits of generators. Now you have this one. Power balance at each bus N. So if you have 3 buses, you are going to have 3 power equality constraints. So let's see what that equation say. What is this equation? It says that all the power that leaves from bus N to other connecting buses. So since we are saying it's like power that leaving that bus, it looks like a demand. So all demand in that bus plus all the power leaving that bus should be equal to the all generation in that bus. So that shows all the demands in that bus. This is all the lines connected to bus N and all the generators connected at bus N. And lambda N is our LMP, nodal price at bus N. Then we have the capacity line constraints. Are you following me? F is the capacity of the line. We have one extra constraint saying that select one of the nodes and enforce the voltage angle of that node to equal to 0. We call it reference node. It could be, for example, bus 1. Why do we do that? It's a mathematical reason. For AC power flow, there are technical reasons. In here, I mean, this is not AC power flow equations anymore. We slaughtered that. It's only a mathematical reason. Because now we have more variables than constraints, we make one of the thetas equal to 0 to have the same number of variables with constraints. Good. So this is what you are going to solve it for nodal system. For zonal, even we don't want to use the DC one. We don't care at all about Kirchhoff's laws, Ohm's laws, not at all. We only use NTCs. Who gives us that? TSOs or RCCs. And we simply say the flow, the trade between zone A and B is between, okay, here instead of NTC I used ATC, but they are interchangeable. Between ATC and minus ATC. For example, between Denmark, DK2, and Sweden 4, SE4, you can trade between 1,000 and minus 1,000. No power, no susceptance, no grid data at all. For example, it could be saying that symmetric NTCs, power flow from A to B, zone A to zone B, is between 2,000 and minus 2,000. It means you can send power from A to B 2,000 or opposite direction again 2,000. But also it could be asymmetric. Not because of physical reasons, it could be security reasons or whatever. It could be asymmetric, saying that from A to B I got 1,000 max, I gonna send maximum 2,000, but in the opposite direction maximum 1,200. You should ask RCCs or TSOs, why do you do that? Clear? So how to transfer nodal to zonal and make it simple? You eliminate all the constraints related to DC power flow. You also eliminate theta, showing voltage angles. Instead, you just simply say F from A to B, power trade from between zone A and B. And simply now, there is no grid data anymore, no susceptance. Just you say you can transfer power from A to B as much as you want, as long as it's between NTC and minus NTC. It's fully unaware of network. That's how we use it in Europe. Again, all demands located at zone A, all zones be connected to zone A, all producers located at zone A, and this is the zonal price. 5 minutes. You see that zonal market clearing, how network unaware it is. So there is an alternative to the NTC-based zonal market. It has been started in CWE, Central Western European TSOs, in 2015. But Nordics just started that in last November. They slightly improve zonal model with NTCs. I'm going to tell you very rapidly. So they like to say that, okay, Zonal market clearing ignores all transmission lines inside the bidding zone. But if I have a critical line inside in Germany, I have to reflect that. So we try to impose transmission line capacity of critical lines, that the domestic lines inside the zone. But we still like to have one price per zone. It's still one price for all Germany. It's still one price for whole DK2. How can we do that? It's a nice mathematical challenge. And still we like to keep the model linear and convex. What we do, we add extra constraint in form of polyhedral constraints. By the way, what I'm saying is just for your information. It's not part of your assignment. It's not. But it's good to know because it's a very hot topic. So this is a slide I got from Jakob, my colleague from, my former colleague now at Nordic RCC. What we do is that we add extra constraints, polyhedron constraints, to our market clearing problem. Each of these constraints reflects one critical line inside bidding zones. So extra constraints. Good. This is what I got. It's a screenshot from Nord Pool. They may look a lot of text, but let's read it together quickly. It says flow-based capacity constraints represent limits on critical network elements in the power grid. So if, for example, in Germany, you have a critical line, you like to reflect the capacity of that line in the market clearing problem, in the zonal market clearing problem. You need to define something called RAM. It's remaining available margin. For example, for that critical line, it's 100 megawatt. Who decides that? TSOs. How they decide that? You can read it in the document. So we have a RAM for every critical line. Then from linearized power flow, you get something called PTDF, power transfer distribution factor. What does it show? Every PTDF shows that how much a bidding zone's net position contributes to the load of the critical network element. For example, you have a critical line in Germany. PTDF of DK2 to that line shows how much the net position in DK2 changes the power flow in the critical line in Germany. It's a parameter. It's not variable. Nordic RCC or TSOs, they give you that number. So the only extra constraints we add to zonal market clearing problem is this one. One linear constraint per critical line. It's simple. The right-hand side is RAM. For every line, you will say my remaining marginal capacity is 100 megawatt. What is the left-hand side? It says PTDF of zone 1 times net position 1 plus PTDF in zone 2 times net positions of zone 2. So you see that how the net position of different zones, they contribute to the line flow of a critical line, the flow in the critical line. And what is net position? The net position is defined here. It's the total export minus total import in that zone. And then we ask Euphemia to include these extra constraints for us in the market clearing problem. Extra constraints. For example, if you check the Nord Pool, you can see that for today, 17th of February, the past hour, the past hour, 2 to 3 p.m., you can see the list of the critical lines. So every line, every row is a critical line. You can see that what is the RAM, the remaining available margin, and PTDFs. So this data provide you extra constraints to include in your zonal market clearing problem. Good. You can do lecture. You can do step 3 now. It doesn't need to have flow-based market coupling. It's only zonal and nodal. Do you have energy for Kahoot? Let's do that. Okay, let's get started. 99. 1, 2, 3. Which one is wrong? The answer is below. The market time unit is currently set to 1 hour, not 30 minutes. The others are correct. The gate closure is noon, day D minus 1, correct. The market time unit will change to 15 minutes in June 2025, correct. It's based on uniform pricing, correct. So ST is number 1. Question 2. About stack, which one is incorrect? Correct. The wrong one is green. It takes, I emphasized, it took around 16 minutes, not 5 hours, to solve the optimization problem for stack. So the first one is correct. We use euphemia. It promotes effective competition, increases liquidity, and the daily value of trade on average is 200 million euros. But the optimization problem takes only 16 minutes, not 5 hours. So Paul is leading. Quiz 3. The system price is 102. What does it mean? Yes, the majority found the right answer. It's unconstrained market clearing price. If there was no grid limit, the marginal price was 102. Still Paul leading. Quiz 4. Which statement is wrong? The blue one is wrong. SE2 price was low, 40, because of congestion. If there was no congestion, the generators there, they can transfer their power to other zones. It's like W1 and G1 here. They couldn't transfer the power to the other side because of the congestion. If there was no congestion, they could transfer and the power and the price could be higher. I understand it's a bit tricky question, but fantastic for those who found the right answer. Good. Manu leading now. Quiz 5. Prices and congestion rent. Capacity is 90 megawatt. Very good. The majority found it's not congested. So price at 2 nodes are 35. Then the price in both sides are the same. So the price difference is 0. The congestion rent is 0. So yellow is correct. Sul. Quiz 6. Now the capacity is 70 megawatt. The same question. Capacity is 70. Well, in bus 1 it's 30, bus 2 is 35. The price difference is $5, €5, and the flow is 70. 70 times 5, congestion rent is $35 or euros. Okay, green was tricky one, Riyad, huh? Okay. Manu is back to number 1. Quiz 7. Which one is correct? Yeah, yellow is correct. Red and blue are wrong. Red says total demand, total payment by demand equal to, it should be equal to congestion rent plus total payment. Right? And blue is wrong. It said it's not budget balance. No, it is. We discussed. It is budget balance because what you get from demands is the same equal to what you pay to TSO for congestion rent and what you pay to generators. Yellow is correct because if the system is congested, the grid owner is paid. Okay, it seems that today questions are a bit tough. X is leading. Question number 8. Very good. We have 3 nodes, 3 nodal power balance. Done. It doesn't matter how many generators lines we have. Diego. Quiz 9. People are responding very fast to this one. Very good. We have 3 nodes, so we have 1 LMP per node, so 3 LMPs. It doesn't matter how many producers, line demands do we have. Still Diego. Quiz 10. Very good. If we add AC equations, the optimization problem becomes non-convex. Done. Red is wrong because it's not convex. Yellow is wrong because we cannot guarantee the solution to be globally optimal. And the green is wrong because we can obtain local solution. Just we don't know if it's local or global, but we can determine the solution. Schwartz is leading. Quiz 11. Which one is not, which approximation is not considered? Very good. Unit susceptance. So what is we ignore, we make it 0, is conductance, G, not B. Diego is back. I think Diego is the one who also got the top in the first quiz, the first Kahoot. Quiz 12. Yes, blue. If we add DC equations, red is wrong. Its optimal solution is never AC feasible. Blue is correct. The solution is definitely globally optimal because it's linear and convex. Yellow is wrong because it's not nonlinear and non-convex. It's linear and convex. And green is wrong because it's not nonlinear. It is linear. Manu is back. Quiz 13. The NTC-based zonal model, what does it enforce? Yellow is correct. Red is wrong because when we use NTC-based zonal, we ignore everything inside the zone. No power flow equations, no transmission capacity lines. NTC only sees the NTCs between the zones. So the only CVC is that inside a zone, in the zone, like Germany, total production is equal to total demand, and also, what comes or leaves Germany as a zone. Vincent is our new leader. Quiz 14. This is a tricky question. You have 45 seconds to think. In which one you need lowest to the highest redispatch? Very good. Very nice, red. Those who selected red. When you use nodal AC, you use the true power flow equations. You don't need redispatch anymore because you represent the true power flow equations. When you go nodal, still you see the nodal representation of the network, but simpler. So you need more redispatch. Then when you go zonal flow-based coupling, you don't see nodal structure at all, just zonal, but you try to add the transmission line capacity of critical lines. And zonal NTC is the worst. You don't model at all the power flow equations, so to restore feasibility, the grid feasibility, you will need a lot of redispatched actions. So red is correct. Matthew, 15 seconds to the last. Multi-select. Which one are correct about flow-based coupling? Very good. Red is correct. Still, there is one price per zone. That's why we have flow-based market coupling. Blue is correct. It reflects the capacity limit of critical domestic lines to some extent. Correct. Yellow is wrong. The zonal prices can no longer be different. Of course, it can be still, if there is congestion. Green is wrong. It removes the linearity. No, it preserves the linearity. It keeps the linearity. Matthew is leading. Last question. Wow. Everyone is fast. Good. It's in Copenhagen. Let's see who is our winner. Number 3, Malf and Mick. Number 2, Noah. Number 1, Matthew. Is Matthew here or online? Matthew? Enya and Matthew from EPFL. Again, I remember Enya also got last time. So very good. We have another, again, winner from EPFL. Thank you, everyone. And, see you next lecture.